Okay, hello and welcome to the Daily Space for Friday, June 8th of 2018. I am your host, Dr. Andres Plazas, and today we're going to bring you a run-up of news from space and astronomy. So today we have two stories. One is, give me a second, one is relatively recent and the other one is a few months old, but I figured I would like to talk about it a little bit. So first we're going to talk about the pillars of creation and magnetic fields in pillars of creation, so what is known as the pillars of creation, and in the second story we're going to talk a little bit about gravitational lensing again. And as you may know, I like gravitational lensing. Um, so for the first story from today, we have the VISTRO survey. VISTRO stands for B fields in a star forming region observations, and B we call B fields the magnetic fields. So the VISTRO survey has for the first time mapped the magnetic field in the dense gas region of what is called the pillars of creation. So they used instruments on the James Maxwell telescope in Hawaii, James Clerk Maxwell, the Scottish physicist. So this is a telescope in Hawaii, and this is a telescope operated by the East Asian Observatory. Well, this pillar is very famous. It's in a region called Messier 16, star forming region. And this is a region that is also known as the Eagle Nebula. It's one of the most iconic images taken by the Hubble Space Telescope, by the HST. So, what are the pillars? The pillars, they are a set of columns of cold, dense gas. They are protruding into a region of hot ionized plasma, so they are surrounded by this ionized plasma. And the cool thing is that these pillars, they have nurseries of new stars forming at their tips. They are a particularly dramatic example of a feature found in many regions of interstellar space where you have stars of high mass forming. So in this study, the researchers, they claim that this is the first high-resolution observation of magnetic fields within the pillars, and how the way they do it is that they look at light in the submillimeter wavelengths. Why do they look at light in the submillimeter wavelength? Is because the cold and dense dust gas emits most of its light in this particular wavelength. So they look at what they call the polarization of light. So as we know, or may or may not know, the light, you can think of it as an electromagnetic wave. It is an electromagnetic wave, and that means it's a transverse wave. And what it means is that it's moving in space and it has electric fields and magnetic fields oscillating perpendicular to this direction of transmission. But this oscillation of the electric field, it could happen in different planes. But the thing is that when the light interacts with the magnetic field, is going to be polarized in a certain direction. That means it's going to have the direction of oscillation of the electric field of the light is going to have a preferred direction. And that in turn is going to let you map the magnetic field within this region. So the light emitted from these dusty regions is polarized in a way that is perpendicular to the direction of its local magnetic field. So these researchers have used these observations to directly prove the magnetic field morphology within the dense gas of the pillars of creation for the first time. So one of the things that they found is that the magnetic field actually runs along the length of the pillars at a significantly different angle to the field in the surrounding plasma. And it has a strength that is more or less intermediate and more or less not too weak but not too strong for a region of space that is forming stars. But one of the implications of these findings actually is that they suggest that the pillars have evolved due to the strength of the magnetic field, and that the pillars themselves are held up thanks to the magnetic support. They suggest that the stars could be formed by the collapse of clumps of gas being slowed down by magnetic fields and resulting in a pillar-like formation, as you can see in the image. Let me see what you guys are saying. All right. Okay, just checking the chat a little bit. But I have another picture related to this story. So this second picture, it actually shows the just to finalize the story, it shows the idea that the researchers have on how this shaping is taking place, right? How is this working? So they say in panel number A, at the left, they say that a front, an ionization front, that is you can see it by the black line in that panel on the left, is moving perpendicular to the ambient magnetic field, and it is approaching an existing overdensity in the molecular gas, and that overdensity is that ellipse, that dark blue ellipse that you can see a little bit below the red arrows, the ionization front. But then when this ionization front is coming, then it's going to be slowed down by this overdensity. And then the magnetic field actually starts to bow into the forming pillar, and that's what you see in the panel and in the middle in panel number B, that is a pillar formation. Then the compressed magnetic field in the pillar helps support the pillar itself against further gas pressure and the own gravity of the pillar, so it prevents it from collapsing by itself. But it cannot support the erosion actually that comes from the top from ionizing photons. So at the same time it's providing support, but then it's telling us that with time the support is not going to be enough because there's going to still be erosion coming from the surrounding environment. So in this cartoon, what I just explained was, of course, panel number C. But in this cartoon, in general, as I said, the dark blue represents the molecular gas, and the light blue represents the ionized material, as I said. The ionization front is shown as the black line, and the gray dashed lines indicate the local magnetic field direction. So you can see how the magnetic field starts to be reshaped by this front. The red arrows are actually representing the pressure from the photons, the photon flux. The black arrows in panel C represent the magnetic pressure going towards the wall of the pillar, and the green arrows represent the actually pressure from the thermal gas from the surrounding environment. So I thought that this was cool because it's for the first time they show a mechanism through which actually these pillars of creations are actually being held, and how they are triggering star formation. And as I said, this is one of the most famous images taken with the Hubble Space Telescope. Not only in the visible, but now we're also imaging it in other wavelengths such as the submillimeter. Okay, that was the first story for the day, and the second story, as I said, has to do with gravitational lensing. So I was actually probing the archive. So for those who don't know, in astronomy it's very common to write a paper, and of course you want to send it to a journal, so it is peer reviewed. But even before that, sometimes you post your paper on the internet, and hopefully you can get feedback from your peers, from like informal feedback. So it is also a way of making the research accessible to the whole community, because unfortunately sometimes you find out that you're going to read a paper and it's behind a paywall, and that's not good in my opinion, because sometimes most of the research is funded by public funds, so it should be open access. But in astronomy we have this unspoken pact, so we post our papers on the archive while they are being reviewed. Of course, it's always good to have an official journal to peer review your paper, but anyhow, as I said, I was looking into the archive and I found this website is called the Archive, ARXIV, if you guys want to look at it, for those of you who don't know. The point is, I found a paper called the Hubble constant from the supernova Repstal. So this is exactly what you're looking at in this image. So let's back up a little bit. So we have here an example of gravitational lensing. So as I said before in other emissions, so gravitational lensing is a consequence of general relativity, which is the theory of gravity that is accepted today, that it has more has had more experimental success. And this theory tells us that any distribution of matter or energy is going to bend the space-time around it. So if you have a cluster of galaxies, that's a distribution of matter, of energy, and then you have a background source, then here on Earth, then you're going to observe that the image of the background source is going to be distorted, and depending on the geometrical alignment between the observer, the source, the observer, and the lens, you could have multiple images. So this is analogous to a regular glass lens, right? That's what it's called lensing, hence the name. But it's caused just by gravity, by the distortion of space-time. But you can produce multiple images of the same source galaxy, because that means that the one photon of light from the source galaxy is traveling along one direction around the lens, and it comes to you, and then another photon of light is going to travel through along a different direction, and then it's going to be bent by the galaxy cluster, by the lens, and then it's going to come back to you, and that's why you see multiple images. But sometimes it happens that the actual physical distance that the photon of light travels is going to be different. So that means that the image from one of the images from the source is going to arrive either first or later than the other image. It's going to be a delay. So there's going to be a delay because of this geometrical factor. It's just more physical space to advance for one ray of light in comparison to the other. The cool thing about general relativity is that it also predicts something that is called time dilation. So this is what you see in the movie Interstellar, when these people go to a planet next to a black hole, and then it turns out that they spend there only 1 hour, but then they come back to Earth and it's like 7 years. It's because when you're close to a black hole, the gravitational field is actually dilating time. So here we find something similar. In addition to having that time delay because of the physical differences in the distances, you also have a different time delay because of the different strength of the gravitational field along the galaxy clusters that is causing the bending of your light. So why is this important? Because you can measure that time delay, and that time delay you can write down an equation of that you call delta t. The time delay could be days or could be years, and this is one of the cool things that I'm going to tell you about. And you can write down an equation for that time delay in terms of your cosmological model. So again, backing up, what's our goal in cosmology? We want to explain the universe as a whole. We want to explain how the universe came to be, what the contents of the universe is, and what the fate of the universe will be. So in order to do that, we have observations, we create hypotheses, we use the scientific method, and then we create our model of how the universe, or how we think the universe works. And today we have something that is called the standard model of cosmology. So this standard model is a set of hypotheses and explanations based on solid physics and based on empirical evidence that depends on a handful of parameters. So you have the same model, but then there are certain knobs. You can think of the parameters as certain knobs that you can change of the model. And one of these parameters is how much radiation do you have in the universe? How much dark matter do you have in the universe? How much dark energy do you have in the universe? And these are very important parameters because 95% of the universe is dark matter and dark energy, and we don't know what they are. Another important cosmological parameter of this cosmological model is what is called the expansion rate of the universe, or the Hubble constant. So about 100 years ago, Edwin Hubble showed that the universe, that galaxies were moving farther away from each other, and that the velocity of galaxies, it was actually proportional to how far away they were from us. And that constant of proportionality, he called it, well, we call it afterwards, Hubble constant. Actually, it should have been called after Lemaitre. It was Georges Lemaitre who actually discovered this, but for historical reasons, it ended up being called the Hubble constant. And I'm telling all this story because these observations that I'm showing here are actually is another way of measuring this Hubble constant, this expansion rate of the universe, in an independent way, and that's good. The more ways we have of measuring cosmological parameters, the better. So what are we looking at in this paper? In this paper, instead, our background source is not a particular galaxy. It is actually a galaxy, but within the galaxy there was a star that exploded, and this type of star we call a supernova. It's a super bright star. Supernova, super bright. And you can actually see, if you look at the image, you can actually see 4 images of that same supernova, and they form a cross, and we call this the Einstein Cross in honor of Albert Einstein, who wrote the theory of general relativity. And the idea of this type of paper was to measure the time delay between the 4 images. That means the time of arrival, the relative time of arrival between each one of those 4 images. So this was something actually that was seen for the first time in 2015. And actually the idea came from a Norwegian physicist named Refsdal in the 60s. And he said, oh, you could use these time delays from multiple images of supernovae or some other object to measure the Hubble constant. He figured this out in the 60s, and then until 2015, 2014, people were able to obtain this observation that we're looking at with the Hubble Space Telescope, with what is called the frontier fields, where you actually take all the power of the Hubble Space Telescope and look for a long period of time to a galaxy, the largest galaxy clusters in the universe. And then if you look very carefully, then they were able to find this Einstein Cross, and then this supernova was named the Refsdal supernova. It turned out that the time delay between these 3 images, between these 4 images, was actually, the initial time delay was actually of about a few days. But the cool thing is that people actually were able to do a model of the system, a model of the cluster. The most of the mass of the cluster is dark matter, so we don't know exactly the mass distribution of the cluster. But what we can do is that we can create a lot of models and then try to use general relativity, make some predictions, and then try to match those predictions with what we see. And then the model actually said, there should be actually another couple of images that should come back in a year. And actually that's what happened. A year later, people observed another time delay of another image of the same supernova. It was another time delay because it took the bundle of rays of light from that image took a different path, but at the same time suffered a different time dilation depending on the geometry of how far they were from the center and of the strength of the gravitational potential. So in this paper that I found in the archive, it was published in January or February of this year. For the first time, they provide an estimate of the Hubble constant using this method. And the cool thing is that, okay, they gave an estimate of this Hubble constant. And nowadays within the cosmology community, there is a debate within the action value of what is the actual value of the Hubble constant. So back in the time, Hubble himself, he measured the constant, and he measured it to be a value of 500 kilometers per second per megaparsec. So maybe don't pay a lot of attention to the units for now. Units are important, but just don't get distracted by that. But you can think again of the Hubble constant as the proportionality between the velocity of a galaxy and the distance from us. Hubble measured about 500, but then with years and with decades, we were narrowing down the value of this Hubble constant to be closer to about 70 kilometers per second per megaparsec. So again, we came from 500 to 70. And then within the experimental errors, we were more or less happy, like, oh, okay, I think this experiment gets 71, this other experiment is getting 69, plus or minus the error bars, because we actually have intervals when we have a description of a cosmological parameter. And there was an agreement, more or less. But then came better experiments, and this is how science advances. When you make better experiments, better observations, then you're able to reduce your error bars, and then you can see, maybe there's something else going on here. And the thing is that you can use experiments of the local universe that tell you what the value of the Hubble constant is, but also you can use measurements from the very early universe, when the universe was a baby, like when the universe was about 300,000 or 400,000 years after the Big Bang. So let's remember that the universe, the age of the universe is about 13.7 billion years. So you can use measurements from the early universe, from the cosmic microwave background, to then put constraints on your cosmological model, and then you can extrapolate using, you can use the cosmological model from measurements of the CMB to produce a prediction of what the Hubble constant should be. But then you can also do independent measurements in the local universe, like closer to our age. And by local, I mean like 5 million years ago, 4 billion years ago or something like that. And people have been finding a discrepancy. People actually have been found people that measure the Hubble constant with the CMB, they claim that the Hubble constant should have a value of about 67 kilometers per second per megaparsec. Whereas people measuring the Hubble constant in the local universe, they claim it to be about 74 kilometers per second per megaparsec with a certain error bars. So there is a little tension. There are other experiments that say no, actually the constant is about 77 kilometers per second per megaparsec. And at this point, you guys might be thinking, oh, we're splitting hairs here. But this is important because if we actually found that the Hubble constant from what we get from the CMB and from what we measure in the local universe, if we found that these values actually are different, then it could point out to a dark energy that is actually changing in time. So in another episode, I commented that the universe is expanding, but it's expanding at an accelerated rate, and we have no idea. It's expanding faster and faster with time. But as I said, we have these cosmological models that is self-consistent logically. So you can write down equations where if you can change this Hubble constant, it can also give you information about the amount of dark energy, which is another very important parameter of your model you want to know about. So it's very important to settle down the difference between these two values from the early universe and from the local universe. So, well, the answer that this paper gives is like, oh, we found something that is actually consistent with both data. So they found something of the order of 64, I think. Yes, like of 65 kilometers per second per megapixel. Actually, they find something that is more or less more consistent with measurements of the local universe. But as I said, all these measurements, they come with intervals. So it's what in the technical jargon you call it to be like 1 sigma away or 2 sigma away if you assume that your errors have a Gaussian distribution, but it's usually more complicated than that. So for the moment, some people say yes, there is a tension, but then some other people say like no, this is statistical. This could be also due only to a statistical or a systematic error that you haven't taken into account, and that could be it. But just to wrap up, this technique is great because this result that I'm showing today is actually in agreement with the theory of general relativity, which we always like that's good. We also like it when things don't agree with the theory, because that could signal new physics. But we're also happy when a theory passes a test. So again, this is a prediction from general relativity that is more than 100 years old. Then it's a prediction that was calculated in the 60s, and it was measured in the 2000s, in 2015. And it's a new method. For the first time, these people did a calculation with this new data from the Hubble Space Telescope from this actually for this cluster, and they made these new models of the clusters, and it gives us another tool to calculate the Hubble constant. So, well, that's what I wanted to say today. I like gravitational lensing. I did my PhD studying systematic errors in weak gravitational lensing, something another regime of gravitational lensing. But maybe I can let me see, guys, if you have any comments, and let's see what you guys think. So somebody says that the Hubble constant from Planck studies of the CMB is lower than the recent value from Gaia. Is it due to an effect of dark energy over time? It could be. So that could be an option. So we don't know for sure yet, but that's an option, as I was saying. If we find a difference, it could be that dark energy is actually changing over time, and this is fundamental because we're trying to do like kind of baby steps in order to understand the dark energy. And one of the first steps that we want to know is like, is it constant over time? Is it consistent with a cosmological constant, which is mathematically equivalent to the energy of the vacuum? So the simplest explanation is to say that this dark energy thing has an energy density that is constant in time. As more space-time is produced with the expansion of the universe, this substance, the energy density of this substance remains constant. So this is one of the things that we want to try to figure out with surveys like the Dark Energy Survey or the Hyper Suprime Camera Survey or Pan Stars and all these current surveys that are the surveys that are happening right now. But then there's gonna come another generation of surveys such as the WFIRST, the Wide Field Infrared Survey Telescope, if it doesn't get cancelled by NASA, by the executive branch of the government. There is also the Euclid spacecraft by the European Space Agency, and then there is the Large Synoptics Survey Telescope. And these surveys also have as an objective try to determine the nature of dark energy and to see if it changes with time. So we should be able to get better data and to see if through the history, the cosmic history of the evolution of the large scale structure of the universe, it points towards a dark energy that could change with time. Yeah, Larry posted a link to DES, the Dark Energy Survey. Peter is excited about the organic molecules in Mars. I think, yes, Pamela talked a lot about that yesterday. I'm excited as well, but we have to be careful. Science also advances in small steps. Do you do much research with CMEs? What is CMEs? So I guess that tells you no. But what is CMEs? I'm sorry. Ace and win the spacecraft to find discrepancies. Ah, cool. Maybe, yes, I don't know what that means. So you're saying, so Corn on the Con says, thank you for the stream. Do you do much research with CMEs? My answer is I don't know what those are. And he says, or she says, or they say, I have been working on correlating data from NASA's ACE and WIND or WIND spacecraft to find discrepancies. I don't know what those are. Maybe you can explain, and sorry for my ignorance. But yeah, thank you for your comments. I'm looking back. I know I need to get better at look at the chat when I'm talking, but I guess I'll focus and then I just don't look at the chat until I'm done. And the other day I was talking and nobody was hearing, and I should have looked at the chat to you guys. So the Vikings discovered America before Christopher Columbus did. Yes, you could say so. the Chinese. But then what do you mean discover? No, there were already people here. So, um, but yeah. Anyhow, I'm just looking at your comments. Looks similar to a Celtic cross too. Uh, Maybe. I guess. Yeah. Sometimes the Celtic crosses that I've seen are like a little bit more geometrical or have more curvature. Could be. Um, do I have a link to the archive paper for the gravitational lensing story? Yes, I do. So you can. The cool thing is you just go to the archive. It's arxiv.org. Archive. I'm gonna write it in the chat. ORG. If you go there and then you type the number of the paper. Every paper has a single identifier given by the date. 1712.05800. So that's the paper I was talking about. The cool thing is that the other day I was looking at my email and then somebody from LSST sent another email saying that they had done a similar analysis a few months later, saying that no, these people from the paper that I talked about, no, these people didn't do a good modeling job, and actually we did a better modeling job, and that's okay. That's how science works. Like we try to improve on measurements. So I'm gonna put the number of that paper as well if you guys are interested. Co da, 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 da. That's the name of that's the number of the other paper. You go to archive.org and the number of the paper is 1802.01584 by Claudio Grillo from Italy, I think. Yeah, so yeah, go ahead and check out the paper, and they actually do. They can tell you about all the details that I didn't talk about the Bayesian analysis and about the modeling. A lot of the effort in this type of research goes into the modeling of the system itself, of the mass distribution within the cluster. Because once you have that potential, that mass distribution, you can plug that into general relativity and then make your predictions of multiple images. And then you also have the constraint that all the multiple images that you see in your system, they must belong to a single image in the source plane. So that is giving you more information, and then you can put that information into your mathematical model because you say all these images, they should have the same origin, and that gives more information to your likelihood analysis is called. And yeah, so that's why it's cool. Okay, everyone. Okay, that's it for today. I had these two stories that I wanted to share. Thank you very much for watching. This has been the Daily Space. Is a production of CosmoQuest created by the Astronomical Society of the Pacific. Please, if you like this show, give us a follow. It's good to have follows. It helps support us. But at the same time, please consider subscribing or contributing to our Patreon and all the stuff. That'd be great. And next up on this channel, we will have Dr. Matthew Richardson. And yeah, so please stay tuned. The Daily Space will be back next week. Probably Pamela. But once in a while, it will be me. So I hope you guys are not bored with me. But yeah, thank you. Have a great weekend.